Welcome back to another AP Physics 1 topic overview. Today we're going to be talking about elevators in Newton's second law. So let's get right into it. Just to start off, any of these facts and examples will be in the description down below as Google Docs. Starting off here with our facts, we are going to have acceleration. Acceleration is going to end up helping us create our Newton's second law equations later on. So what exactly is acceleration? It just tells us how much an object's speed changes in 1 second. The main two ideas with this: when an object increases speed, its acceleration is in the direction of its motion, and when an object decreases speed, the acceleration is in the opposite direction of motion. So acceleration is not just in the direction of motion, it depends on whether I'm increasing or decreasing speed. My units are going to be meters per second, telling me again that my change in speed every second is acceleration, or just meters per second squared. Then Newton's second law, some of those ideas, just a general forces idea. For all other forces other than the force of Earth, the objects must be in contact in order to experience that force. Then we have that object's acceleration is in the direction in which forces are unbalanced. That just means wherever the force is greater, that's the direction of acceleration. Net force is the same thing as an unbalanced force, so they can be used interchangeably. And that bullet below, fairly similar to the bullet before, unbalanced forces in the direction of acceleration. And my equation for this, unbalanced forces equal to F net, same exact thing, is equal to ma. So let's move into some more facts. So how do we actually solve Newton's second law problems or problems with forces? First off, we're going to start off with a free body diagram. Always, that's going to help us create these equations or what forces we're going to have in the equation. Then we're going to write two equations, one each direction if needed. Up forces minus down forces equal to ma. Left forces minus right forces are equal to ma. You can also start off with the F net equals ma to have that understanding that F net is up minus down or left minus right. Note with this, you don't want a negative force, so you're going to start the equations in the direction of acceleration. So instead of this, where I have up minus down forces, that would be the acceleration is upwards. If my acceleration was downwards, I'd reverse that and do the down force first in the free body diagram minus the up force equal to ma. Then what is a free body diagram, or what does it include? It's going to include an arrow representing each force. Each arrow begins on the object. We have a dot for that, and points in the direction in which the force acts. Then we have a list of forces to the side, talking about the object applying the force and the object experiencing the force. So let's go into our last page of facts here. Talking about our last page of facts here, this is just a little bit of refresher. Mass and weight, remember these are not the same exact thing. Mass is in units of kilograms. It tells us how much material is contained in an object, while weight is actually the force of the planet on the object. That's going to be in newtons. To go from mass to weight, you multiply by g, the gravitational field strength of that planet. On Earth, it's 10 newtons per kilogram. Then you have normal force. Normal force is the force of a surface on an object in contact with that surface. It's perpendicular to the surface, and a scale or a platform scale or a force plate is going to read the normal force. So if we're trying to find the reading in a scale, it's actually asking us to find the normal force, not my actual weight, the mass times g. That's going to actually, my normal force is going to be different if I'm accelerating in some way. So let's move into our example now. Moving into our example here. Again, this example is linked in the description down below as a Google Doc, along with the facts that we were going over in the previous slides. What we have here is a physics teacher with a mass of 75 kilograms is standing on a scale in an elevator. The elevator then increases speed, moving upwards with an acceleration of 0.50 meters per second per second. On the dot below, we're going to draw and label all the forces acting on the physics teacher while in the elevator. This is our free body diagram. So again, with any free body diagram, we're going to first assume that we are on Earth unless otherwise stated. So the first force that I should always have is going to be the weight of the object, or Fg. And last time I checked, if I drop something, it is going to fall straight downwards. So that's going to end up being Fg, straight downwards. Now for our list of the object on object, what is the object actually creating gravity? Gravity is not an object itself, so we're not going to say force of gravity on my teacher, the planet that we're on creates this gravity. And since we're on Earth, we're going to have the force of Earth on the teacher. Now all my other forces must be contact forces. The only thing I'm in contact with is the scale. The scale is going to push up on me. It essentially acts as a surface. So we can call that a normal force because it's a force of a surface on my teacher. And that's going to act perpendicular to the surface straight upwards. So what's the object that creates this force is going to be the force of the scale on the teacher here. So that's going to be my normal force. Those are my two forces on the teacher. So let's now move into part B of this example. All right, so moving into part B, what's the direction of the elevator's acceleration? And we're going to justify our answer. So again, when justifying anything here, we're going to do our ERC, start our evidence, our fact of physics, our reason, our explanation of the situation, and then our claim, essentially just our answer. So with this situation, we have an elevator that's increasing speed, and therefore the physics teacher are increasing speed while moving upwards. So that means we can start off with a motion or kinematics fact for acceleration. We haven't really been told that the forces are greater in one direction or the other, so we gotta use kinematics for this. And our fact is going to be here that when an object increases speed, my acceleration is in the direction of motion, or the object's acceleration is in the direction of motion. We can then have our reasoning. What's exactly happening here? We know that the elevator is increasing speed while moving upwards. So we can say since the elevator and therefore the physics teacher are increasing speed while moving upwards, that's going to be my reasoning. I can then make my claim. I'm increasing speed while moving upwards. I know that means that my acceleration is then in the direction of motion. So I can say there that my acceleration is also directed upwards for both the physics teacher and the elevator. This is going to help us either explain how forces are going to change or create our Newton's second law equation if we're going to do that later on in this example. So let's move into part C. Alright, so looking at part C, we're going to explain the situation qualitatively, which just means the explanation and not really math related. As the elevator increases speed while moving upwards, you take a look at the reading on the scale. Is the reading on the scale greater than, less than, or equal to the weight of the physics teacher? So again here, looking at our free body diagram, we're just going based on earlier. The reading on the scale here is my normal force or my upward force. That's going to change whether I'm accelerating upwards or accelerating downwards or just moving at a constant speed. Fg is only going to change if I move to another planet or I move very far away, because Fg is just my mass times the gravitational field strength on the planet. So we're looking at here my normal force, whether it's going to change or whether it's going to be greater than Fg, whether it's going to be less than Fg, or etc. So in order to explain this, we got to talk about direction in which forces are unbalanced. So I got my explanation, I'm going to have here my evidence, my reason, and then my claim, which is my answer here. So my evidence here, since we're talking about direction in which forces are unbalanced, and we know the direction of acceleration, we can say that acceleration is in the direction in which forces are unbalanced. That's going to be my evidence here. Then we gotta talk about our reason here. We figured out in part B that my acceleration was directed upwards for both the physics teacher and the elevator since they're moving together as one. So we can say here, since the acceleration for both the physics teacher and the elevator are directed upwards, we can then make our claim, which is going to talk about the upward force and the downward force. So we know here the upward force, Fn, or the force of the scale on the teacher, must be greater than the force of Earth on the teacher here. Because the upward force is the direction in which forces are unbalanced, that means that's a greater force. So that's going to then tell us that the scale should end up reading greater than 750 newtons here. So again, direction in which forces are unbalanced are upwards. That means since our acceleration is upwards, the greater force should be the upward force. That's the force of the scale on the teacher. That's going to give us the reading on the scale. That should then end up being greater than the weight of the teacher, Fg. So that's going to end up being my claim here, the upward force, the force of the scale on the teacher, must be greater than the force of Earth, better known as weight or Fg, on the teacher. This means the scale should then read more than 750 newtons. So our checkoff here on this question is going to end up being greater than, as our direction in which forces are unbalanced are going to be upwards. So let's then move into our math portion, our quantitative portion of this example. All right, so part D. We're going to calculate the reading on the scale as the elevator increases speed while moving upwards with an acceleration of 0.50 meters per second per second. So when it says calculate the reading on the scale, we know from our facts earlier that the normal force, that a platform scale actually reads the normal force. So that's what we're trying to solve for here. And we're dealing with forces and acceleration. We're going to be dealing with Newton's second law. So again, Newton's second law is unbalanced forces equal to the net force, which is equal to ma. Unbalanced forces and F net are the same exact thing as the up forces minus down forces, or left forces minus right forces, depending on what my free body diagram and direction of acceleration is. In this situation, we only have up and down forces, so that's all I'm going to have here for my net force equal to ma. Then for this equation, we know that we're going to start off with the force that's in the direction of acceleration. So we know from earlier that my direction of acceleration was upwards. So I'm going to have here up forces minus down forces are equal to ma. And then that's where my free body diagram really comes in. What's my up force and what's my down force? Again, my up force here is the normal force, or the force of the scale on the physics teacher. So that's going to be a force I'm going to put in here. That's what I'm going to be solving for at the end of the day. My down force here is Fg, or my weight, and that is equal to ma. So the normal force Fn minus Fg is equal to ma. Then while I go one step further, plug in what the equation is for Fg. I know the equation for Fg from my facts here is m times g. So we have then the normal force, or the force of the scale, minus mg is equal to ma. Now the ultimate goal is to get normal force on one side of the equation all by itself. So since we have attached to it mg by a subtraction sign, I'm going to do the opposite operation and add mg on the both sides of the equation, and be left with my normal force, or the reading on the scale, is equal to ma plus mg. Now I can plug in numbers and plug into my calculator and end up with my answer. So for this, my normal force, or the reading on the scale, is equal to the mass of the physics teacher, which is 75 kilograms. Then I have my acceleration, which is given to me as 0.50 meters per second per second. Then I'm going to add on again the mass of the physics teacher times g. G is again 10 newtons per kilogram. So I can plug this all in here. Normal force is equal to the force of the scale is equal to 75 kilograms times my acceleration, plus again 75 kilograms times the gravitational field strength. Now all you're going to do is plug this into your calculator. You're going to end up with 75 times 0.5. That's going to be 37.5. And that's going to end up as newtons for my units. Same exact thing there for 75 times 10. That's 750. Add them together, you should end up with an answer here as 787.5 newtons. As you can see, when I'm accelerating upwards, my force of the scale, or my reading on the scale, is going to be greater than the weight at rest, which is 750 newtons. So we see here that physics works. We can prove this through our math and our qualitative reasoning from earlier. So I hope this example was helpful, and see you guys in class.